We are going to program the planet motion, Earth around the Sun, using or solving these four coupled first-order differential equations. How? Here we are going to do it sort of the dirty way. First crude method you will typically use given any problem. It's an Euler scheme. First order forward Euler. Say, take the first one. We say x derivative equal to something. X derivative with respect to time. So then we say x derivative is roughly the same as x new minus x old divided by some delta t equals, and here in my example, equals to u. And for this one to be a first order forward Euler, then also this u value has to be the old one. So there you see it's an explicit expression for the new unknown x in the future based on just old values. So we rewrite this one to say x new equals x old plus delta t multiplied with the right hand side of the equations. Here is just u old. That's it. So I am now going to program this one. Let's see. I need a new script. And I start the same. Clear all, close all, CLC. Then I save this one and I save it as planet. Planet underscore Euler. So in any program you start with all your constants. Here we don't have that many constants. I have the parameter g multiplied with big N equals 1. This is also a trick. When you have a problem, ordinary differential equation, or partial for that matter, you don't really know what's going on. You want to simulate this, you want to program it. But you have no idea what the values for the different parameters should be, and you have no idea of the physics, how he behaves. Think of it as a non-dimensional form. You just put all the parameters, all constants, equal to 1. Then you will have a time scale of roughly 1. Then most of the physics is going to take place in a time scale of 1. That's a very convenient way to start. Then you can also choose now a value, reasonable value for the time step. That's your choice. You have to give him a number. But if you know the time scale is 1, then you can now say delta t then should be 0.01 or something. Then he should resolve the time scale, more or less correct. So start with unity for all parameters as a first simulation. Then you can play around with the code and do some simulations and see how they behave. Before then, later on, you can start punching in real numbers if you want. So here I just say 1. I have to simulate this one for a certain amount of time. So the maximum time, say 100. Why not? And that now should be roughly what I need for constants. I need initial conditions for my problem here. What was it? I had the Sun and the Earth. X, Y, position R. So for the planet, you need a start position. And again, I choose 1 for the x-axis. And then I say y equals 0. So there I have my starting position. Then I need to give him some start velocities. Velocity in the x direction is 1, and the velocity in the y direction is, oh sorry, not 1, 0. If I now choose 0, what's going to happen? Well, that's a very bad idea, at least for us here on Earth. The planet is going to go straight into the sun. Very bad idea. So I have to give him a sort of a velocity upwards. 0.5. Or let's start with 1. Just for fun. So that's my initial condition. You need numbers before you now begin. Then I need sort of the forward loop, the time loop, the main loop here in this program. And a bad way to do it is the following. For time t equals 0 with step delta t all the way up to t maximum. Yes, you can do this. Don't do it. It works, but you should never use real number in a for loop as a control here, because delta t, he might be very strange numbers, 0.0, 1, 2, 3, 4 or whatever, then it might not fit here. And you are really not certain, do we hit Tmax exactly or not? You don't have any control, any good control. So you shouldn't use the real numbers as a counter. So what you then can do, use an integer. Typically we will use I as a first counter. I, j, that's also a little bit sad, but it's for historical reasons. In other languages, Fortran, C, always use I as a counter. Here in MATLAB, I, sadly, is predefined as a complex number. It's the square root of -1. But when you use it, then, of course, he will be redefined. So frequently you will find I and j as counters. So here I want to go from step number 1 all the way up to, how many time steps do I need? Well, I need this one as a real number, maximum time divided by the chosen time step. This also might not be a real number, sorry, an integer. It can be anything. So here you should use either round or ceiling. I think it's ceiling is what I choose here, wasn't it? Yes. So the highest integer that fits this ratio. This is much more neat. So we won't shoot you if you do with real numbers. Still okay, but you should do it properly. Okay, now we have the initial state at time equals 0. Then find the new everything. First of all, then I need the radius. And actually, I need him to the power of 3. So here, if we want to do it straightforward, we do it as follows. Radius is the square root of x square plus y square, like that. Then I have r, and then I need r to the power of 3 afterwards. So that should be okay. Now I need finding new x, new y, new everything. And here I do it crudely. I overwrite the values in the simulation. I don't store the values old and new all the time. I just overwrite it. So that can be a little dangerous, but then much easier to program, save storage and everything. I don't want to store all the old positions. I only need the latest. So I overwrite the values. So the recipe says delta t multiplied with u. Like that. Same goes with the y. T times v. And then u equals the old one plus delta t multiplied with, and then we have the entire expression here. That was g minus first, gm multiplied with an x divided by radius to the power of 3, like that. Copy this one and insert for v, same recipe, but then it is y I need, like that. So now I have updated the values, position and velocities, and I can create a plot. I want to see the position, plot x comma y. Now if we stop here, we can do this. It should work. Let's see what happens. Well, MATLAB is busy, you can see down here, but I don't see anything. So this is rather boring. So click down in the command window and Control C. Control C kills your simulation. Control D in Linux, or Control Z, even harder kick to stop him. But Windows, Control C. So nothing happened. First of all, here what I'm aiming at is to have an animation. I want to see the motion of the planet during the simulation. So to do that, I have to tell MATLAB to draw now, or else he won't do it. He's lazy. So that's the first step to make it run. Now let's see what happens. Well, at least he's doing something, but we don't see much. You see the scale changes all the time, but the plot that he's actually doing is just one single dot, and it is so small that you don't see it. I can kill this window, but it doesn't help. It just pops up again. So again, down here, Control C to kill him. Of course, down here I can plot something else than the default, just a single dot. That's 1 pixel, which is so small that you don't see it on the screen. So here I can say plot blue circle. B for blue, O for a circle. That should help. Yeah, now something is happening. But I don't really get it. So we kill that one also. What do you have to do? Well, before you begin, you have to create a figure. Figure, just call him 1, that's okay. And then you can say plot the initial position, x, y, blue circle, and then you write hold on. That means all following graphics will go into the same window without destroying what's there already. So that will be valid until he hits hold off. Now at the end of my program I can always write hold off. That is not necessary here because I only have one window, and when the program is finished he's going to find hold off anyway. So, but you need hold off if you have several windows and you want to update this one, this window a little bit, and then you want to update the next window, then you need hold on, hold off, switch window, hold on again, and so on. So hold on, hold off, they are sort of belongs together. Now let's see if this one works. Yeah, it works, but he operates rather strange. Also, he rescales the window all the time. I don't like that. So let's kill him again. You can kill the window, doesn't really help. So Control C. So what else do we need? Well, we need the axis. Axis, you specify then the minimum x, the maximum x. And here it should be between -1 and 1, both in the x and the y direction. Then you should sort of fix the window scale. And now run this one. Now it's more like it. So this is the very, very crude way to do it. What is sad here is that he can start out nicely, but he's going to go slower and slower and slower and slower. But it makes a very nice circle though. Very good. But this way to make an animation is bad. Every time he now prints a new one, he has to print all the old ones as well. So it's a very, very bad way to create an animation. As a first check, you can do it like this, but I won't recommend it in the end. Very, very bad indeed. So let's kill this one. Well, still doesn't help. Kill it like that. Now let's do this differently. I want to have, hold on. I want the sun as well. Plot in the position 0, 0. We plot yellow, no, not yellow, red circle, like that. And for the planet, here, you give a name to this graphical object, this circle. You call him something. This is allowed in MATLAB with plot or line or surface or whatever. Call him an h equals and then semicolon. Why should we do that? I'll show you. I run the program and I crash it, and then I write whose. So here now I have a list of all my variables, and you see this h. He's actually something. It's a MATLAB graphics. It's sort of a pointer into a graphical object. And this h, that is something we can play around with later on. If you write here in the command window get h, then you can get a list of all properties belonging to this graphical object. And it's a long list. So here you can play around with, during the simulation, you can change all this. You can change the color, the size, and more important for us, you can change the position. You see he starts with 1 and 0. So now we can play around with that one during the simulation. Then you don't need 1 million different planets to make an animation. You just change the only one you need to sort of describe it. Another way to do it could have been inside the code here. After you have plotted the original, before you plot the new one, you can plot the old one with white color. Then he disappears. And then instantly you plot the new one in the new position. Then you will have an illusion of an animation. But MATLAB, stupid as he is, he will always redraw all the old values, and your program is going to go slower and slower and slower. So here, instead of this plot sentence, remove this one, and we say not get but set h. I want to change the values, the properties to this graphical object h. And what I want to change is, here you have to use in quotes, x data. We now have the value x, and y data has now the value y. and then draw now. So now we will only have one single planet, and he should then orbit quite nicely around the Sun. Let's see if this works. There we go. And this one, he won't slow down as time goes by. You only have these two graphical objects. So that is how you can easily create an animation. Now back to the program. This program is actually wrong. It's not correct. That's too bad. That's too bad. Well, before we look at the error in it, I want to have a marker here. Let's see if we can do that. Yeah, we could use some modulus here. Mod, say for every 100 time step. If this one equals to 0, then we can plot x, y, and then a small little blue dot. And just for cosmetic reasons, I can show you the effect of that one. So for every 100 time steps now, he will draw a small little dot. So when you do several orbits, we can then see, do we get a constant orbit or does it change? So that's one way to do it. Looks like he hits the orbit quite nicely, actually. Now, back to the program. It's wrong. Can anybody tell me why this is wrong? This is not the Euler scheme, the first order forward Euler scheme. What is wrong? Can anybody see the error? I mean, I programmed it as it's written on the blackboard. Should be correct, shouldn't it? Now remember how MATLAB thinks, how he works. You do the program sentence by sentence. And here I programmed it so I overwrite all the values. Here I create a new x. Here I create a new y. Here a new velocity u. Should be based on old values. This one is not old. It's just been updated in the same time step. This one should be the old value, not the one I have created here. It should be the one that I had from the previous step. I can't do this. It's wrong. So what should we do? You can baptize these, and you can do it for all of them if you want. Now the two velocity expressions should be correct. They are based on the old x and y. And then after I have calculated them, I have to update x equals now x new and y equals y new. Now it is first order forward Euler scheme for all four differential equations. You see the difference? For us, this is actually quite sad, because the error was quite smart. Very good error. So you can see now, if I rerun this one, because you see from the simulation, the planet goes around the sun in a perfect circle here. So he's going to go like this forever, no problem. Now let's see what happens if we do it with the correct numerical scheme. We run again. It starts out nicely. Oops. Then it disappears. Come back again. Oops. And this is just going worse and worse and worse. So what's happening here, the planet is moving away from the sun, which is not the case. You shouldn't do that. It should be a perfect circle. So the first order Euler scheme is very bad in this one. I can do the same simulation. That should be one remedy to help it out, to make just a smaller delta t. I mean, the smaller delta t you have, the more accurate this one will be. So reduce the time step factor of 10. Then this is going to take forever. But yes, it will be more accurate. But it will not help. The planet will still drift away from the sun. And you can use as many zeros as you like. It will still be bad. So the adder that we made, that I made on purpose, of course, in this code was actually quite smart. But then this code is sort of, it's not called Euler anymore. It's not called Hoin either. It's a second order method. It's something called Störmer-Verlet, I think it was called. Verlet was it, yes. They were dealing with these planetary motions many, many years ago. Actually, I think it was before the war, wasn't it? Yes, many years ago. So they had really fun with this one. But this is not a code then that we were going to teach you. So you have to do it like this. With if we ask for an Euler code, yes, you have to write it like this. Although here it would be smart actually to do this mistake. That's just say for a coincidence. Let's see, he's still running. Let's stop him. If we go the other way, and then we need some more space here, I think. Say 0.5, 0.5. 0.5. You see he disappears very rapidly. So then we are getting a very cold winter quite soon. So now if I kill this window, the program will crash, because now you then destroy this graphical object that you are changing in your simulation. So that's actually a more convenient way to stop the code. So no, this is not so easy problem. How to solve it more accurate then? What we are going to also deal with in this course, it's more advanced than this Euler scheme, which then, as I said, is just first order accurate. So we have more advanced schemes than this one. So what we, well, I don't need that one actually. What we then are going to use is MATLAB's built-in solver for ordinary differential equations. It's called ODE45. The documentation is fairly impressive. And for all these doc pages, normally you will look at the syntax, how to use these codes, how to use these functions, and then you skip all the description because it's too boring and too many strange words in it. Then you go all the way down to examples, how to use this. So much easier. And to use this ODE function, that's an Runge-Kutta fourth order method, but he uses a fifth order to assure the correct order of 4 in the solution. Also, he will provide, or he will find the proper time step himself automatically, depending on the solution. I mean, if you have a problem where the solution goes something like this, and then all of a sudden like this, and then smooth again, he will find that, okay, I can use big time steps here. It doesn't change too fast. But here I really need many small delta t's to resolve the behavior. He finds that automatically, so he's very efficient. So UDE45, that's sort of the workhorse, you might call it, for all these problems. To use it, well, we have to provide him with a function. So I can give you here a quick recipe how this can be done. Let's see, we can close this one. I call this one now planet ODE45. Save. I can use most of the code, but I skip all this. Well, actually, these sentences I want to keep. Skip all this one. And I don't need that one either. Here. Now the syntax goes as follows. T comma y equals. When you have used the function, he will return to you a timetable. You find a solution on all of these different times. So this will be a vector, many different time steps. The y here will be a matrix. Here I have 4 equations. So in this example, he will be a 4 by the number of time step matrix. So the solution will be inside this y matrix. A little sad that they always use y. I mean, I have used y already up here, but never mind that. So you call him by saying UDE45. UDE45, then the first thing he needs, that's the name of a function that we have to create. Swirl alpha, call him func. Next, he's going to need the time interval. When do you want the solution? Well, I want it from time 0 up to maximum time. Second, he needs the initial conditions, which we have provided here. And now the sequence is essential. If I say x, y, u, v, then I have chosen the correct sequence that I want. This is then equation number 1, this is equation number 2, and so on and so on. So the sequence here defines the sequence that you have to use in your function. That's important. Now let's jump to the function. New script, and then the function. First, a name. That's just an internal name, dydt, for instance, whatever. Just a name that the values that this function has to return to my program. Then equals, and here you need to specify or to use the exact same name that you used in the ODE call. This is going to be the file name for this function, so it's going to be func.m on the hard drive. Inside here, you have to use at the time first, and then an array of any unknowns. Sadly, again, they always use y. Just to trick them, I use a big Y. MATLAB differs between large and small letters. So I say a big Y here because I want to use Y in my equations. Whenever you are using this, I will always recommend to translate the variables that you will be given in this vector. So the first one, that is x. Position. That's my first equation. So he will then be y number 1. The position y, that will then be number 2. Oops, like that, and so on. u equals then y number 3, and finally parenthesis, thank you, v number 4. Like that. Then we have to provide him, this function, with the right hand side of the equations. So dy dt equals the first one, that was x dot, that was my first equation, x dot equals y. The next one, that was y dot, the velocity in the v direction, that was just small v. Third one, that was x dot, he was minus g m multiplied with x divided by radius to the power of 3. And then finally minus gm multiplied with y divided by radius power 3. And finished like that. Now he will return 4 values, the 4 derivatives, the right hand side of my equation system. That is what TEP4280 is going to need. He's going to ask this function, how big are the derivatives at this time, given the initial values here? Find the derivatives, give me the derivatives. He's going to need them during the simulation. Here in this function, of course, I have to provide him with the radius, square root x squared plus y squared. And I'm going to need to provide him with the value of this parameter gm. Here, of course, I could have hard-coded gm equals 1. That's not so nice. Constant should always be given in the main program, so here I use a global sentence to tell him get the value from the parameter gm from the main script. Then you have to put him into a global sentence. That's it. That should be enough. So try to save this one. He suggests then the name func. That is quite okay. Back to the main script. Here I then have to give this global sentence here also. And you have to do it up here before you give the value to the GM, or else it doesn't work. Also, don't put him all the way up here, because clear all, then he blow the memory, then he has forgotten all about global. So it must be after these initial statements, and then before you actually start to do something. Let's try to run this one, just to see what happens. Yeah, we did something, and we didn't get any errors, but he didn't plot anything. So he only plot now the red sun. So what else should we plot? Hold on. Well, I want to have the position. I want to plot the orbit. Well, what's the orbit now? Well, the orbit will be inside this matrix, the y. So y, well, I have to write it like this then. Take all of the first ones, that should be the x position, versus all of the second ones. That should be it. Now let's see. Then you see TEP4280 has problems. He can't do it. He doesn't do it too bad. He starts here in 1 and 0. And then actually now the planet is moving towards the sun, becoming hotter and hotter. Well, that's true, isn't it? But no, of course this is wrong. How can you deal with it? Well, you have to tell TEP4280 actually to shape up. You can't use the default accuracy here. You have to sort of squeeze him a little bit with options. Here you use set. That's a function where you can change the default values. He has several you can play around with. Relative tolerance. What did I use here? 1e to the power minus 8. And also obs tolerance. And here I went all the way down to minus 10. So this is really demanding for higher accuracy. And then you tell TEP4280 to use these options. So now hopefully we should get a better result, as you can see. But you really have to squeeze him to make this one work. So calculating planetary orbits, planning a trip to the moon and back again, you really have to use quite accurate methods or else you're in trouble. Okay, any questions? Yep.
In the function made, you have a t.
In the function, yes, we have a t. That's correct.
T before anything?
Now, you see, we don't use it here. That's correct observation. We don't need it. Nevertheless, it has to be stated here. If I remove it, then he's going to kill me. Just have a look. So just save this one and try to run it. You see, added. So in these equations that I have here, my equation system, the right-hand side, they were given, as we call it, as an autonomous system. You don't have time explicit. If you have another problem, say the double derivative equals a force as a function of time, equals cosine omega t, for instance, some variable force with respect to time, then you can use it. Then you will have an expression including t here. So you might say they have put t for that purpose in the event that you actually may need it. Here we don't need it, but it still has to be defined. You see the yellow line here, so MATLAB suggests this one is not used. Remove it, but you can't. It has to be there. Other questions? This is something then you might play around with as a beginning in exercise number 2, where we then are going to look at not planets, but magnets, how they can behave. You can think of the problem if we had a twin sun. You have two suns and then one Earth traveling around them, maybe in between them. That's a chaotic system. Actually, our whole solar system is chaotic, meaning extremely sensible to initial values. And sooner or later, this is going to go wrong. In the future, one of the planets, maybe the Earth, is going to hit straight into the sun. It's going to go bad, or two planets are going to collide. Luckily for us, the planet system is stable within a time span of some 100,000 years, so it's not any immediate danger. But on a long scale, time scale, with 9-10 planets and a sun, it's going to be chaotic. So it's impossible actually to predict correctly. So with two suns and one planet, you can try it if you like. Then you will see it's going to go totally bananas. And you can then change the delta t a little bit, get a totally different answer every time. That will be the topic for exercise 2. Okay, then we stop here.